Chapter 9. Process Preventive Controls for Human Food. Parameters and Values, including Critical Limits, Monitoring, Corrective Action. Process preventive controls make up the part of your food safety plan that focuses on controls required at process steps that are critical for the safety of the food. Process preventive controls require documentation of parameters and minimum or maximum values, e.g., critical limits, associated with the control, monitoring procedures, corrective action procedures, and validation that the process controls the hazard. The requirements for process preventive controls depend on the role of the process control in the food safety system. This chapter provides information on establishing values for processing parameters, e.g., critical limits, how to monitor process preventive controls, and components of corrective actions to be taken for process preventive controls when deviations occur. Link to hazard analysis. Process preventive controls include parameters and usually limits, maximum or minimum values, associated with the control of a hazard. These science-based values are quite specific and are commonly called critical limits. They are applied at processing steps that are frequently called critical control points, CCPs. A CCP is the point, step, or procedure in a food process at which control can be applied and is essential to prevent or eliminate a food safety hazard or reduce such hazard to an acceptable level. Once a process preventive control, such as a CCP, is identified for a specific hazard, parameters and values that can be used to control the hazard must be established. Keep in mind that the requirements for process preventive controls depend on the role of the process control in the food safety system. A variety of formats can be used to document this information. This course uses the format above, which includes information that must be documented in the food safety plan. Details on information required on food safety plan records are discussed in Chapter 14, Record-Keeping Procedures. As illustrated above, the steps identified as requiring a process preventive control, including CCPs, along with the hazards requiring a preventive control, are transferred by the food safety team from the hazard analysis form to the first and second columns of the process control form. This form may be referred to as a HACCP chart if desired. The food safety team then lists parameters and critical limits, the minimum or maximum values associated with the parameters, for the controls for each hazard, all elements of monitoring, corrective actions to be taken when deviations from the critical limit occur, verification procedures and records in subsequent columns. This chapter discusses critical limits, monitoring and corrective action elements of the process control form. Elements of verification and record-keeping requirements are addressed in separate chapters. For simplicity, the term critical limit is used in the rest of this chapter instead of minimum or maximum values associated with the parameters to control the hazard. Critical limits play an important role in a preventive control program. If a hazard exists, it is important to understand values for the parameters that must be met to control that hazard. This chapter focuses on how to establish science-based critical limits that help to assure process control. Sources of information on limits are readily available, and these will be discussed later in the chapter. The chapter also discusses different options used to establish a critical limit, as well as the advantages and disadvantages of these approaches. More conservative operating limits, e.g., higher or lower temperatures than needed for safety, may be useful during production to minimize failure to meet a critical limit and may be set for meeting quality standards. Finally, the chapter shows how to begin to complete a process control form. For most process-related preventive controls, measurable parameters can be identified and the values established for these parameters are called critical limits, defined in the slide. The critical limit must be met at the process control, or CCP, to significantly minimize or prevent the hazard requiring a preventive control. If a critical limit is not met, the step is out of control, i.e., a deviation has occurred, and the potential for producing a product that presents a consumer health risk exists. Examples of parameters that may have critical limits identified include time, temperature, flow rate, line speed, product bed depth, weight, viscosity, moisture level, water activity, salt concentration, pH, and others, depending upon the process. Finally, the chapter shows how to complete a process control form. A number of sources of scientific and technical information can be useful in establishing critical limits, as discussed in Chapter 7, Resources for Food Safety Plans. FDA and other government agencies may provide information through technical staff, regulations, guidelines, directives, performance standards, tolerances, and action levels. Trade associations, process authorities, industry scientists, university and extension scientists, and consultants can provide expertise and guidelines. Scientific studies for specific products can be conducted in-house, at a contract laboratory, or at a university. Information can also be obtained from peer-reviewed scientific literature. Use care when applying information from these sources to critical limits for a specific product and process. There may be important differences between the methods used in a published study and those used for the product and process under consideration. The critical limits may need to be adjusted to account for those differences. For example, higher fat levels may have a protective effect in the microbial lethality of a heat treatment, which may require a higher temperature or a longer time to achieve the same level of kill compared to a lower fat product. Because of the potential safety implications, meeting critical limits at a CCP is essential for the safety of the product. Because of this, it is important that the critical limit can be achieved by the process. A critical limit is generally expressed as a parameter equal to or above, or below, a critical value and not at the specific value itself. For example, processing equipment could not easily maintain the exact value of exactly 160 degrees Fahrenheit or 71 Celsius, so the critical limit would be set at equal to or greater than 160 degrees Fahrenheit or 71 Celsius. This allows the CCP to be achieved and gives the option of exceeding it, say for being more conservative or to operate at a higher processing limit. Many times, different options can be applied as critical limits to control a specific hazard. The food safety team decides the best option for the particular CCP, taking into account practical considerations such as the process capabilities in question, how measurements can be made, staff capabilities, and other appropriate factors. There are many different types of critical limits. They must be specific for the CCP and the hazard that is being controlled. Different critical limits may be needed for ingredient-related hazards and process-related hazards. Each CCP must have one, or more, critical limit for each food safety hazard, as illustrated in the examples above. An effective critical limit defines what can be measured or observed to demonstrate that the hazard is being controlled at that CCP. For example, both time and temperature measurements may be elements of a critical limit to eliminate food safety hazards such as pathogens at a cook step. Facilities may have different options for controlling a particular hazard. The selection of the best control option and the best critical limits is often driven by practicality and experience. As illustrated in the slide above, critical limits may involve a number of parameters such as time, temperature, airflow, product weight or thickness, and the like, depending on the nature of the product and the process. Some facilities may choose to use a higher airflow and a reduced thickness in the dry product example to achieve the end point more quickly. These parameters must be determined on a product-by-product basis and consider the role of the control in the food safety system. A variety of approaches could be applied to set critical limits for a cooking CCP intended to eliminate the hazard of vegetative pathogens in a frozen omelet. In the example above, the product temperature achieved during cooking is set as the critical limit. However, the product temperature may not be easy to monitor for each individual product cooked. Heat transfer rates during cooking could also vary for several reasons. For a sauce, measuring the product temperature may be practical because the liquid could be mixed. For a product like an omelet, a procedure would need to be developed for measuring the temperature of an omelet. If it is a batch process, e.g., baked in a set of pans, this may be workable. However, if each omelet is individually made, it may be less practical to measure temperature and record temperature because the time for doneness may vary from one omelet to the next. One would need more assurance that the critical limit is met for each individual product. Except in limited circumstances, e.g., the product is a liquid such as milk in a pipe or a continuously stirred liquid product, it seldom is practical to continually monitor the temperature of each individual food product on a processing line to ensure conformance with a critical limit. As an alternative, the example above establishes conditions necessary to ensure that the cooking process achieves the minimum product temperature and time. In this approach, the oven temperature, the belt speed going through the oven, and the volume of batter placed into standard pans are all factors that affect the final temperature. These parameters are easy to monitor and measurements are obtained quickly to determine that critical limits have been met. A scientific study, validation, discussed below and in Chapter 13, verification and validation procedures, must be performed to ensure that controlling these factors at the specified critical limits will always result in an internal product temperature that will destroy pathogens of concern. Typically, this option provides better assurance and may be easier to perform than the previous option, even though more parameters must be monitored at this step. The E.G. Food Company's hazard analysis described in the previous chapter identified 2 CCPs, including 1, the cook step, and 2, metal detection. Cook, this is a CCP for inactivation of vegetative pathogens such as Salmonella. In this operation, each omelet is individually cooked by an operator. Based on validation studies, see Chapter 13, Verification and Validation Procedures, the food safety team determined the critical limit for this CCP. Omelet temperature is 158 degrees Fahrenheit 70 degrees Celsius instantaneous before transfer to assembly table. This critical limit is entered in the process control form. Metal detection, this step is a CCP for metal that may have been introduced earlier in the process. The food safety team identified metal detection as a CCP, with the critical limits: 1. Metal detector present and operating, and 2. No metal fragments that would cause injury or choking are in the product passing through the metal detector. This critical limit is entered in the process control form. It is essential that the critical limit selected actually controls the identified hazard. This requires application of science to validate that the control is effective. The process of validation is discussed further in Chapter 13, Verification and Validation Procedures, which includes an example of a validation study conducted for the E.G. Food Company. This section covers the definition of monitoring, as well as explaining why it is important. Considerations for designing a monitoring system are discussed, as well as different methods that can be used. Monitoring is a preventive controls management component that applies not only to process preventive controls, but also to allergen and sanitation preventive controls, as appropriate to the control and its role in the facility's food safety system. Monitoring involves the selection of appropriate measurements or observations at a specified frequency to provide information to assess whether a control measure is operating as intended. In other words, to conduct a planned sequence of observations or measurements to assess whether control measures are operating as intended. The purpose of monitoring is to document that the minimum or maximum values, such as a critical limit, for a parameter have been met, thus ensuring the food safety hazard has been controlled. Monitoring also provides data to document that products were produced in accordance with the food safety plan. It is important that monitoring procedures are specific for the parameter identified in the food safety plan. When monitoring shows that the minimum or maximum values, such as a critical limit, for a parameter are not met, a corrective action is needed, which is discussed later in the chapter. Monitoring requires 4 elements. 1. What measurements or observations will be used to monitor? 2. How to conduct the monitoring? 3. What frequency will be used for monitoring? And 4. Who will do the monitoring? Monitoring process preventive controls depends on the nature of the control and its role in the facility's food safety system. It may involve measuring a characteristic of the product or process to determine if a critical limit is met. Examples of monitoring measurements could include cold storage temperature, when the refrigeration unit temperature is the parameter for which a critical limit has been established. Line speed and cooker temperature, when cook time and temperature are parameters for which critical limits have been established. The pH resulting from adding an acidifying ingredient, when pH is a parameter for which a critical limit has been established. Process parameters such as line speed, flow rate, bed depth, or similar elements, if these have been established during validation, is critical to control the hazard. Observing that the metal detector is on when metal is a hazard of concern. Checking that the sizing bar that controls thickness by rejecting oversized units is in place if thickness is a parameter important for heat penetration. Different methods can be used to monitor critical limits, depending on the nature of the control. These methods need to be real-time and accurate. They should also consider if there are worst-case locations, like cold spots, that must be monitored. If you are using monitoring instruments in the wrong way or in the wrong location, then the objective of monitoring is likely not being met. Using calibrated instruments to measure a critical limit parameter is an effective way to conduct monitoring. Examples of monitoring instruments could include thermometers, pH meters, water activity meters, data loggers, etc. A discussion of calibration occurs in Chapter 13, Verification and Validation Procedures. Monitoring methods can also involve visually checking what you are monitoring. When using visual observation, it must be clear whether or not a critical limit has been violated. In our omelet example, a production employee observes that the metal detector is on and that the reject device is working. The employee records these observations at the beginning, middle, and end of the shift. Monitoring should be designed to provide rapid, real-time results. Some laboratory methods are relatively quick and can be used for decision-making. For example, pH measurements are useful to monitor fermentation processes. Viscosity measurements may be useful for processes that require specific flow characteristics for an effective heat treatment. Brix measurements, moisture content, water activity, antimicrobial concentration measurements, and other types of tests may have application in a food safety plan. However, lengthy analytical tests, such as many microbiological tests, are not useful for routine monitoring because critical limit failures must be detected quickly and an appropriate corrective action instituted before product is shipped. The concept of real-time laboratory methods is evolving. Ideally, it provides immediate results. Sometimes there is a delay of seconds to minutes. It could also include a longer time if the product remains in process or on hold until results are in for decision-making. Tests that take longer can still play a role in preventive controls through verification procedures. See Chapter 13, Verification and Validation Procedures. When possible, continuous monitoring procedures should be used. Continuous monitoring is generally performed by an instrument that produces a continuous record. These records can be either affirmative records demonstrating temperature is controlled or exception records demonstrating loss of temperature control. See discussion below on exception records. The record needs to be checked by an individual periodically to ensure that the critical limit is being met. The length of time between checks directly affects the amount of rework or product loss that may occur when a critical limit deviation is found. Examples of continuous monitoring could include: the time and temperature data for a batch pasteurization process may be continuously monitored and recorded on a temperature recording chart. The temperature of a storage cooler may be continuously monitored and recorded by an instrument at a predetermined time interval. A functioning metal detector automatically monitors all product that passes through it. Oxidation/reduction potential, ORP, is recorded continuously by a calibrated automated probe in a vegetable phloem. The proper functioning and automated records generated, if any, for each of these types of systems must be monitored or verified, as appropriate, see below on exception records, by an individual on a periodic basis to document that the system is performing as specified in the food safety plan. For example, the ORP readings may be read twice a shift by a line operator in addition to the continuous record. The term continuous monitoring may be interpreted differently by some. In this course, continuous monitoring can be performed by a device itself as long as a visual check of the data and/or functionality, as appropriate, is also performed to ensure that the device is functioning properly. Charts run out of ink, pens get stuck, and probes can malfunction, which is why human involvement must occur periodically. In many situations, continuous monitoring systems are not feasible because the technology does not exist, the cost is prohibitive, or other reasons. It is still necessary to establish a monitoring interval that ensures critical limits are met. The frequency of non-continuous, periodic, monitoring could be influenced by historical knowledge of the product and process. Questions that could help determine the frequency include, which is why human involvement must occur periodically. How much does the process normally vary, e.g., how consistent are the data? If the monitoring data show a great deal of variation, the time between monitoring checks should be short. How close are the normal operating values to the critical limit? If the normal values are close to the critical limit, the time between monitoring checks should be short. How much product is at risk if the critical limit is exceeded? If a large amount of product is at risk and cannot be reworked, for example, more frequent monitoring may be prudent. Examples of non-continuous monitoring include temperature checks of batter on a breading line at specified intervals if a continuous monitoring system is not feasible. Water activity measurements for batch process operations, antimicrobial chemical levels, and a vegetable flume when automated monitoring systems are not available. Exception reporting involves automated systems that are designed to alert operators and management only when a deviation, in other words an exception, from the requirement is observed. Automated exception reporting may be more efficient than that performed by operators, allowing increased sampling frequency, often continuous, and reduction of human error. For example, refrigeration temperature control can notify on exception, e.g., high temperature alarm, and may only record temperatures that exceed the specified temperature. Such systems must be validated and periodically verified to ensure they are working properly. With such systems, monitoring records may not always be necessary when validation and periodic verification are conducted to ensure that the system is working properly. Therefore, records of refrigeration temperature during storage of food that requires time/temperature control to significantly minimize or prevent the growth of or toxin production by pathogens may be affirmative records demonstrating temperature is controlled, e.g., a chart recorder, or exception records demonstrating loss of temperature control, e.g., an alarm system that records when a deviation occurs. If a facility uses exception records, the facility must have evidence that the system is working as intended, such as a record that the system has been challenged by increasing the temperature to a point at which an exception record is generated. Exception records may also be adequate in circumstances other than monitoring of refrigeration temperature, such as monitoring for foreign material with X-rays, which results in a record only when the system detects foreign material. Validation is required. Individuals assigned to preventive controls monitoring activities must receive training appropriate for the task. They can be line personnel, equipment operators, supervisors, maintenance personnel, quality assurance personnel. Monitoring by line personnel and equipment operators can be advantageous since they are actively watching the product or equipment. Including production workers in food safety activities helps build a broad base of understanding and commitment to the preventive controls program. The monitor's duties should require that all deviations from critical limits be responded to immediately and reported as necessary to ensure that process adjustments and corrective actions are made in a timely manner. Rapid response when operating limits are not met can prevent critical limit deviations. All records and documents associated with preventive control, including CCP, monitoring, including corrective actions, must be signed or initialed by the person doing the activity and the date, and, where appropriate, the time of the activity recorded. Properly trained, qualified personnel must perform monitoring required by the plan. Process control forms must specify who, i.e., the position, performs monitoring. While this may be assigned to a supervisor, make sure this is realistic for the facility. For example, supervisors are sometimes called away for other activities, such as accompanying an inspector during an inspection visit. It is not realistic to expect one person to accompany an inspector and perform monitoring activities at the same time. It is preferable to fully explain the importance of monitoring procedures to a responsible line worker who can maintain the records and even take immediate action necessary when a deviation occurs. For example, a line worker on a final packaging line may be trained in monitoring activities at a metal detector. The individual can investigate detector rejections, kickouts, to determine cause, document findings, run calibration checks, etc. without direct involvement from supervisors. This person could even shut the line down if issues are identified and then inform supervisors for more in-depth investigations. Individuals assigned to preventive controls monitoring activities must also receive food safety training on information discussed in Chapter 14, Record-Keeping Procedures. One more time, monitoring personnel. Qualified individuals are not required to be preventive controls qualified individuals but must receive the food safety training required by regulation and be trained to perform their assigned task. The E.G. Food Company's food safety team determined monitoring procedures for each of the 2 CCPs identified. The cook step is discussed here. Metal detection is available in Appendix 3. As previously discussed, the critical limit for cooking the omelet was determined to be omelet surface temperature is equal to or greater than 158 degrees Fahrenheit, 70 degrees Celsius, instantaneous before transfer to assembly table. Several elements of monitoring are associated with this CCP. Each omelet is cooked individually. A technician or designee, the WHO, measures the surface temperature, the what, with an infrared surface thermometer, the how, for each cook station 4 times per shift, the when, and documents this on the form below. An example of a monitoring record is illustrated above. It provides space to record the data observed during the monitoring activity. While not required, it also includes information from the process control form to ensure that the person who is doing the monitoring activity has the most current information and knows what to do. Monitoring record-keeping requirements are covered in Chapter 14, Record-Keeping Procedures. When something goes wrong, corrective actions or corrections must be performed depending on the hazard and the nature of the preventive control. Requirements vary for process, food allergen, sanitation, and supply chain program preventive controls. This section covers the definition of corrective action and corrections. Deviations from process preventive controls frequently require corrective actions, thus corrective actions are addressed in this chapter, including basic information on record keeping. Corrective actions and corrections are preventive control management components. Corrective actions are procedures that must be taken if preventive controls are not properly implemented and involve documentation of the specific actions taken. Corrections apply when you take action in a timely manner to identify and correct a minor and isolated problem that does not directly impact product safety, such as identifying a food contact surface that was not properly cleaned and re-cleaning it prior to production. Many sanitation preventive control lapses can be effectively managed through use of corrections. Conversely, many process preventive control lapses require corrective action procedures. A food safety plan should be designed to ensure that critical limit deviations are rapidly identified and corrected. When a deviation occurs, it is possible that unsafe product may have been produced. The action take should be appropriate to the nature of the hazard and the preventive control. Thus, in some cases, you may be able to identify and correct a minor and isolated problem that does not directly impact product safety, in which case corrections may be adequate. The subsequent discussion focuses on corrective action. The corrective action procedures must describe the steps to be taken to address the points noted above. The first requirement is to take appropriate action to identify and correct the problem with implementation of a preventive control. This could involve failure to meet a critical limit or a verification procedure indicating an issue. Corrective actions may also be required for certain verification procedures, such as detection of pathogens. Process control must also be restored. Empowerment of employees to stop the lying when they observe a process deviation can enhance food safety and minimize the amount of product that will be subject to review. This requires training and trust, but can be very useful to encourage a food safety-minded culture. Predetermined corrective actions in your food safety plan provide a how-to guide that describes the steps to take when a preventive control is not properly implemented, e.g., a critical limit deviation occurs. The second requirement is to take action to reduce the likelihood that the problem will recur, when appropriate. Root cause analysis may be useful to determine how to prevent recurrence. Corrective action examples may involve equipment repair, employee training, and overall evaluation of the process for improvements. Sometimes this may be a simple readjustment of the process, but sometimes an alternate process is required. Alternate processes must be validated for effectiveness. The third requirement is to evaluate all affected food for safety. Implicated product should be segregated and evaluated to determine if a food safety hazard exists. Product testing may or may not be required, depending on the nature of the hazard and the nature of the process. The fourth requirement is to keep all affected food from entering into commerce unless you can ensure that the affected food is not adulterated, Section 402 of the Federal Food, Drug, and Cosmetic Act, or misbranded with respect to allergen labeling, Section 403(w) of the Federal Food, Drug, and Cosmetic Act. It is best to be cautious, but product destruction may not always be necessary. If a hazard exists, the affected product must be reworked or disposed in a manner to ensure it will not cause consumer illness. Examples of corrective action for the process include those listed above and others. Sometimes an immediate adjustment of the process may be possible. However, for many processes, constant tweaking can increase process variation, which reduces certainty of the overall effectiveness of the process. If an immediate adjustment is made frequently, a follow-up study on the impact on the safety of the product overall may be warranted. As previously mentioned, it may be appropriate for an employee to stop the line. This requires empowerment of the employee to take this action. In some situations, an alternate process may have been validated to be effective at controlling the hazard. If this is the case, such a process may be implemented as a corrective action. For example, if a temperature drops below the critical limit, an alternate process that involves longer time at a lower temperature may be applied, provided it has been validated. Equipment repairs may be required, as well as retraining employees on proper procedures. In some situations, an evaluation of the entire operation may be required to ensure that the product is capable of being produced under conditions that are essential for product safety. Regarding corrective actions associated with the product, a product hold, however brief, is essential when a deviation occurs at a CCP and product has been produced. The product must be evaluated to determine the potential risk prior to making the decision to release, rework, or destroy the product. This may include diverting the product to a different use where the hazard is not an issue, such as use as an ingredient that will be further processed or diverting it to animal food. Appropriate regulations must be followed. Although it may not be possible to anticipate all the deviations that could happen, corrective actions need to be taken and fully documented even when an unanticipated situation occurs. Circumstances considered to be unanticipated problems include: a preventive control is not properly implemented and a corrective action procedure has not been established. A preventive control, combination of preventive controls, or the food safety plan as a whole is found to be ineffective, such as when verification activities detect a pathogen in an RTE product. A review of records finds that they were not complete, activities were not conducted in accordance with the food safety plan, or appropriate decisions were not made about corrective actions. In such cases, in addition to taking the corrective actions already described, the food safety plan or applicable portion of the plan must be reanalyzed to determine whether modifications to the plan are required. As with other products subject to a deviation, proper and thorough safety evaluation is necessary to determine the disposition of the product. Decisions related to the disposition of the affected product must be based on sound evidence. This evidence must be documented to support the decision. Like other corrective actions, if the product is rejected or destroyed, the processor needs to document that this has been done. Whether the corrective action was planned or unanticipated, a preventive controls qualified individual must conduct or oversee review of records for the appropriateness of the corrective actions. Not every firm has an expert on staff who can evaluate the safety of products involved in a deviation. It may be necessary to identify additional resources that can help with product safety evaluations. First, records must document the actions taken to identify and correct the problem with implementation of the preventive control in order to reduce the likelihood that the problem will recur. Included in this requirement is a record of the actions taken to fix the problem that caused the deviation and to restore process control. Evaluation of historical corrective action records can help to identify recurring problems. When critical limit deviations frequently reoccur, the process and the food safety plan may need reanalysis and modification. A formal process may be needed to manage major changes that need to be implemented. This may include reissuing forms, retraining employees, phasing in changes, managing label information, and forming suppliers and other tasks, depending on the nature of the change. Second, records must document how the safety of all affected food was evaluated. Specific technical expertise may be required for this evaluation, depending on the nature of the deviation. Third, records must reflect that all affected food involved in a process deviation was prevented from entering commerce until it has been determined to be safe. This includes identifying the amount of product involved in the deviation, as well as records documenting the disposition of the product. An example of a corrective action form appears above. In some situations, corrective action activities may take place in a short period of time. In other, more complicated situations, corrective action activities may take place over several days, or possibly longer, e.g., capital improvement projects. It is important to have an accurate record of all corrective actions to protect both the public and the product. For example, failure to provide adequate rationale as to when the incident started and ended can lead to an expanded recall affecting a substantial amount of product. Use of an operating limit allows the detection of a potential problem before a critical limit is violated because the value for the parameter is usually more stringent or conservative than the critical limit. Operating limits should not be confused with critical limits. Operating limits are established so that the critical limit is achieved before the operating limit. The process may be adjusted when the operating limit is not met, which avoids violating the critical limit. These actions are called process adjustments. A processor may use these adjustments to avoid loss of control resulting in a deviation and the need to take corrective action. Spotting a trend toward loss of control early and acting on it can save product rework or, worse yet, product destruction. Operating limits may be selected for various reasons. For quality reasons, for example, higher final temperatures than are needed to kill pathogens may enhance flavor or structure development, or may be necessary to control organisms that can cause spoilage. Shelf-stable acidified foods present an example of a process in which operating limits are used, because the times and temperatures required to achieve commercial sterility generally exceed those needed to destroy pathogens that are potentially present. To avoid deviating from a critical limit, for example, a product that must be acidified to pH 4.6 for safety may have a more stringent operating limit of 4.4 to reduce the likelihood of exceeding the critical limit. To account for normal variability, for example, a fryer with a 5 degrees Fahrenheit, 2.8 C, variability should be set at least 5 degrees Fahrenheit, 2.8 Celsius above the critical limit to avoid violating it. The example above illustrates two important points. 1. Operating limits and process adjustments, and 2. Critical limits and corrective actions. In this example of a cooking process, a critical limit is established at 165 degrees Fahrenheit, for e.g. 74 Celsius, plain omelet, and it is following corrective the temperature fell below that limit. Hold product back to the last setting an operating limit above the critical limit. In this example, at 167 degrees determine Fahrenheit, root cause, 75 Celsius, or correct as appropriate. Could have alerted line personnel. This information is recorded in the food safety temperature back above the operating limit. If an adjustment is made before the temperature drops below the critical limit, on controls, no corrective action records that are identified in the hazard analysis. However, as steps in this example can be applied to was not made until after the temperature drops below the critical limit of 165 degrees Process Fahrenheit. Preventive controls are frequently called critical control points. Corrective actions must be taken, and a corrective action depend on the nature of the hazard and the nature of the preventive controls records. Critical limits, i.e., a maximum and/or minimum value to which a process effectively controls a food safety hazard to an acceptable level, must be determined at each process-related preventive control, e.g., CCPs, identified in the hazard analysis. Critical limits must be validated to ensure that the values established are effective in controlling the hazard. Monitoring procedures are required at each of these steps to ensure that the process is in control, e.g., that critical limits are met. Such procedures must specify what will be monitored, how it will take place, how often it will be done, and who will do it. Corrective actions that describe what to do when critical limits are not met must also be determined, unless you are dealing with a minor and isolated problem that does not directly impact product safety. Two additional requirements for process preventive controls are described in Chapter 13, Verification and Validation Procedures, and Chapter 14, Record-Keeping Procedures. Together, these elements help to ensure the safety of food products. Great job completing the lecture. Make sure you check out all the chapter resources. Please complete all activities and exercises. See you in Chapter 10.